2-6, families of functions. In this section, we are going to take a look at families of functions, the simplest form of a function, parent function, and we are going to move functions around the graph. We're going to move them up, up, down, left, and right, and we're going to compress them and stretch them, which are all different kinds of transformations. Okay? So that's our objective, is to analyze the transformations of functions. Okay? And what we should know, our essential understanding, is that there are sets of functions called families, which each function is a transformation of a special function called a parent. Okay, so we'll get into more of that in a minute. But the idea here is that every function is going to have the simplest form of a function, and from there we can make more complicated and more elaborate types of functions from that parent, from that simplest case. So let's look at this problem right here. Okay, so the equation of the line is, the blue line on the right, is 1/3 x plus 1. So if we look at that line right there, right, it has a intercept point of 1, and it has a slope of 1/3, up 1, right 3. Okay? How could you change the y-intercept of the graph so a second equation passes through point P? Well, I could take this line and just move it up. That would change my intercept, my y-intercept to 2, and now it does go through point P. So basically, I took that line and shifted it up. So from right here, how could you change the slope so that the graph of a third equation also passes through point P? Well, instead of drawing a line that had a slope of a +3, let's draw a line that has a slope of -3. So that would be a line that looks like this, which does go through point P. Okay? Now that's not the only line I could do. I could draw through point P. I could draw a line like this. I could draw a line like this. In fact, I can draw an infinite amount of lines through that point, all with different slopes. And if I wanted to go from the blue line to one of the red lines, I saw that all I had to do was move it up and then change the slope, turn it around, and now I have the blue and the red line look the same. So I transformed my original blue line into something that was a different place and a different slope. And that's what we're going to be doing in this section. Okay? We are going to change the simplest form of a line into something more complex, and with other functions as well. Okay? So what we should have gotten out of that quick problem was that different non-vertical lines have different slopes, or y-intercept, or both, and they are graphs of different linear functions. So you can think of one as a transformation of the other. That's what we just said, right? We can think of the blue line as a transformation of the red line, or the other way around, the red line as a transformation of the blue line. Okay? So that brings us to a couple definitions. Okay? So first is that linear functions form a family of functions. And each linear function, each line, is a transformation of y is equal to x. Okay, that is the simplest form of a function of a line that I can get, which means that it's called the parent linear function. Okay? Every single line that I draw can be derived from this equation right here. And if we graph it, okay, there's my axis, my slope would be 1, my y-intercept would be 0, so my parent function line would look like that. Okay? If I wanted to draw another line, I could move this. I could move this line left. I could move this line left. I could move it right. I could move it up. I could move it down. I could change the slope by spinning it around, and I could do a few things. I could change the slope and move it. I could do anything. Okay? I can make any line out of my parent function, out of my parent linear function. Okay, because it's the simplest form of that particular family. We'll get to different families of functions as we move further into the course, but we'll start with the parent linear function. Okay? So each function in the family is a transformation of the parent function, right? We're going to change the parent function around to get any form of the equation I want. Okay? So the first type of transformation that we can do is something called a translation. Okay? A translation shifts the graph of the parent function horizontally, vertically, or both without changing its shape or orientation. Okay? So if you can see here, in my vertical translations, okay, I add in the blue, if I start with the red function and I move the red function up, I get the blue function. And you can see that I have added something to the outputs of the function, and that has shifted the function up. Okay? In the green, I've moved the red function down, so I have subtracted something from the outputs. Okay? So if we have our parent function of f of x, and we add or subtract some number, k, to the outputs of the function, I get a vertical translation. Plus moves the function up, minus moves the function down. Horizontal translations work a little bit differently. So I see that if I add something to the input of a function, I would shift the function to the left. If I add something to the output of a function, I would shift that function to the right. So by adding a constant h to a function inside of the function into the inputs of a function, okay, I would have a horizontal translation. A plus h moves it to the left, a minus h moves it to the right. Okay, and those are translations, left, right, up, and down. Okay, so let's look at my parent function and y is equal to x minus 2. How are they related? How are their graphs related? Well, let's first write down the data for y is equal to x, which would just be the same because y is the same as x, and I have all my x values right there. Okay, so and 2. Now I want to take both of those and or all of those output values, and I want to just subtract 2 from them. So I would get -4, -3, -2, -1, and 0. Okay, so let's graph both of these. Let's graph the parent function first in red. So I have -2, 2, boom, 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 and it keeps going, of course. And so there's my parent function. There's my y is equal to x. Y is equal to x. Okay, so now let's graph this function with my x values and my y values. So at -2, I would be -4, boom, 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 boom. So graphing this line looks like this. Okay, and that is y is equal to x minus 2. And now we can see that I took the red line and I moved it either down 2, if I want to think about down, or right 2. Down, because we have a negative, we have subtracted 2 from the outputs, or to the right because we've subtracted 2 from the inputs. Okay. With lines, they both kind of work a little bit the same because it's tough to tell whether a line is moving up and down or left and right. Okay. Easier to tell with something like a parabola. So if I'm looking at this parabola and I want to translate it up 5 units, okay, I would want to add 5 to the output. So first, I should get the outputs of the original function. So my original function would be 3, 0, -1. I'm just plugging into this function right here, plugging the x's into that function right there, 0 and 3. Graphing that function gives me -2, 3, -1, 0, 1, 0, 3. So that gives me a nice parabola like that. Okay? And now I can I want to translate this up 5 units, so I would just add 5 to each of the outputs. So 8, 5, 4, 5, and 8. And I can graph that, and I would get the parabola then to move 5 up. So let's do it. -2, 4, 5, 6, 7, 8. And 0, 5. Boom, boom, boom. And I can see that if I take the red one and shift it up, whoops, shift it up 5 units, I would match up with the blue one. Okay. So I have successfully translated this parabola up 5 units. Okay, let's look at some of the multiple choice that we did in class. Okay, how are these two functions related? Here's my parent function. Here's my other function. How are they related? Well, this is the difference. So that means the graph is 5 more than my output from my original function, and it means that I'm either gone up or to the right. So I can get rid of anything that says less, okay? And so the answer is B, right? It's 5 more than my output from my original function, which means it's gone up 5 units, not down 5 units. Okay? So next, okay, if we look at this function, if I look at the graph of f of x, it's an airplane scheduled to depart an airport at noon. The plane leaves 2 hours late, which means my function is moved to the right. If I wish to move a function right too, if I start with my original function and I want to move a function to the right, I should subtract 2 from the input. Inside of the function, I should subtract 2. Next, something called a reflection. So my first translation, or my first transformation, were these two translations, a vertical translation and a horizontal translation. Okay, so now we're going to get into a reflection. Okay, reflection flips the graph of a function across a line like the x or the y-axis. It doesn't have to be those two. We can reflect a function across other lines, but those are the two simplest, and those are the ones we're going to do for now. Okay, each point on the graph of the reflected function is the same distance from the line of its reflection as its corresponding point on the graph of the original function. What does that mean? That means that if I look at my original function here, and I look at this reflection here in green, this point is the same distance away as this point. These 2 points are the same distance away from the line, from the y-axis, which I reflected. These 2 points are the same distance away. Okay, and all the points on each function will be the same difference, and they would kind of look like a mirror image of each other, which is the point of a reflection. Okay, now, here, when you reflect a graph in the y-axis, the x values change signs, the y values change the same. Okay, so if we are going to reflect in the y-axis right here, okay, if we're looking to look at the black one and the green one, the x's change, the y's stay the same. The x's change, the y's stay the same. Okay. The opposite is true for when you reflect a graph in the x-axis. When we reflect a graph in the x-axis, the x values stay the same and the y values change. So now, if we look at the blue, look at the blue and the black, right? My y values change. My x's stay the same. Okay, so what does that mean to us? That means that you kind of got to think a little bit opposite. So if you want to reflect something in the y-axis, change the sign of the x coordinates. If you want to reflect something in the x-axis, change the sign of the y coordinates. Okay? And when we're dealing with actual functions, this is the notation that we have to use. So for our function, f of x, for our parent function, whatever it might be, the reflection in the y-axis is I take all the x's and I make them negative. Okay? To reflect something in the x-axis, I make the entire function negative. Okay? I put parentheses around the whole function and change the sign of everything. For a y-axis, I only change the sign of the x values, of the x's. Okay? So very, very different. We've got to make sure that we get those right. Okay? So let's look at this problem. We want to reflect it. We want to let g of x be the reflection of f of x is equal to 3x plus 3 in the y-axis. Okay? In the y-axis. So because I'm going to reflect it in the y-axis, that means that I am going to input negative x into the function. So in order to reflect it into the y-axis, g of x is going to be f of negative x. And that's how I reflect something into the y-axis. So when I want to do this, let's plug in f of negative x. Everywhere there is an x, I plug in a negative x. So my function becomes plus 3, which turns into negative 3x plus 3. And if I were going to graph these two, okay, if I were going to graph these two, okay, let me do the original function right here in red. So my intercept is 3, so I put a point there. My slope is 3, so that's up 3 over 1. Here's my original function. Okay, let's graph this one in green. So now my intercept is still 3, but now my slope is negative 3. So that's up 3, left 1. Okay, so now here's my new function. And we can see that if that was the mirror, right, it looks like I have the same thing on either sides of the y-axis. I've reflected it in the y-axis. Okay? If I want to reflect this in the x-axis, instead of plugging f of negative x, g of x would be equal to the opposite of the whole function, which means that I would start with the whole function, 3x plus 3, and I would put a negative out front, which would give me negative 3x minus 3. Okay, so let's graph this one in blue. So I would start at a negative 3, and now my slope would be, okay, I didn't write the negative, okay? My slope would be negative, okay? So it would look like, this, it would look like that, okay? So now, this is my mirror, right? That's what I want to reflect in. And you can see that the red and the blue are reflections of each other in the x-axis, while the red and the green are reflections of each other in the y-axis. Okay? So this problem right here, if I wanted to reflect this in the x-axis, okay, my answer would be A, because I have to do my new function would be negative f of the whole function, which would be negative 3x plus 12. So this would be negative 3x minus 12. Okay. So we've done horizontal and vertical translations and reflections. So next up is something called stretch and compressions, vertical stretches and vertical compressions. There are also horizontal stretches and compressions, but we're not going to get to them until much later in the course. Okay? So a vertical stretch multiplies all the y values of a function by the same factor greater than 1. Okay? A compression reduces all y values of a function by the same factor between 0 and 1. So if we look at my original function in the blue, the red would be a stretch. When you stretch a function, you pull it away from the x-axis. So this was my original distance. Now this is my new distance. Okay, you pull it away from the x-axis. With the green, and we have multiplied it by a number bigger than 1, by some constant a. Okay, if we look at the green function, okay, we've multiplied it by a number between 0 and 1, some sort of fraction. So what we would do here is we have our original function here. We are pushing it closer to the x-axis. Instead of pulling it away from the x-axis, you push it closer to the x-axis. Okay? So a is going to be bigger than 1 for a stretch. A is going to be in between 0 and 1 for a compression. Don't mistake that with a negative number. Okay? A negative 3 does two things. The 3, that is a number greater than 1. That is a stretch. The negative is a reflection. So a negative and a 3 are two different pieces to my transformation on this graph. Okay, so let's look at a quick function and let's stretch and compress it. So with this function right here, x and f of x. Okay, the table down here, this table, it's not at the right, but this table represents the function f of x. What are the corresponding values of g of x if I want to multiply f of x by 3? So let's figure it out. Well, first, hold on. First, let's graph f of x. Okay, we'll do it in red. So -5, 2. Okay, -2, 2. 0, -3. 3, 1, and 5, -2. Okay, connecting my function looks like that. Okay, so now if I take this function and multiply it by 3 to give me my new function, okay, if I take all my outputs, multiply them by 3, I would get 6, 6 minus 9, 3 minus 6. Okay, and I'm going to graph that in green. So graphing -5, 6 would give me a point right there. Right there. It's 3, 6, 9 right there. +3. And we can see that when I connect all these, I have pulled the red function away from the x-axis. Okay, I pulled the red function away from the x-axis. If I wanted to push the function closer to the x-axis, I could do something like this. That h of x, another function, is going to be equal to 1/2 f of x. So now I can push this closer to the x-axis, and it would look something like that. Okay, to push it closer to the x-axis. Okay? And those are stretches and compressions. Right? If we look at this, which of the following, right? Write an equation for the following transformation of y is equal to x by a vertical compression, a compression by a factor of 1/4. That would be this one. Okay? All we have to do is multiply our function by 1/4 in order to compress it. If we wanted to stretch it by a factor of 4, that would be the answer. Okay? So here's a sort of culmination of all the different types of transformations that we can do to f of x. Okay? Vertical translations. Okay? If we add k to a function, it moves the function up. If we subtract k from a function, it moves the function down. Notice that k is outside of the function. You are adding it to the outputs. Okay? For horizontal translations right here, okay, we are subtracting h from the inside of the function to move it right, adding h to the inside of a function to move it left. Notice that these are kind of opposite of what you think they would be. That a negative moves it to the right and a positive moves it to the left. Okay? That's horizontal translations. Vertical stretches and compressions. Okay? A positive, no, sorry, not a positive number, a number bigger than 1, and you could think about these as absolute values also. A number greater than 1 stretches the function. A fraction or a decimal compresses the function. Okay? And negatives are some sort of reflection. If it's a negative in front of the function, it is a reflection in the x-axis. A negative inside of the function is a reflection in the y-axis. Okay? So 4 major types: vertical translations, horizontal translations, stretches and compressions, and reflections. All of them can move the function all sorts of different ways. Okay? So if we want to look at something like this, the graph of g of x is the graph of f of x is equal to 4x. So if we're going to start with this, okay, and we are going to compress it vertically by a factor of 1/2, and then reflect it in the y-axis. Okay, so I'm going to compress it vertically by a factor of 1/2. I just multiply it by 1/2. And then I want to compress it inside the y-axis. Or sorry, I want to reflect it inside the y-axis, so I'm just going to put a negative inside the function to reflect it in the y-axis. Now I just have to actually input my function. So that would be 1/2. My function, instead of x, I want to write negative x, turns into 4 times negative x. Okay? And then when I work this out, I get negative 2x. Okay? For this question, which I did not write down, f of x would be 2x squared, and g of x would be 6x squared minus 1. So the question is, how do you get from f of x to g of x? Well, I want to turn 2x squared into 6x squared first, and I can do that by multiplying by 3, by stretching the function by 3. Okay? Then I want to take this function and I want to move it down 1, which is where the negative 1 comes from. So to get from this original function here to this function right here, I would multiply it by 3, I would stretch it by a factor of 3, and I would move the function down 1. Okay? Real quick, if we look at these last couple problems, so which function is that reflected about the y-axis and vertically compressed by a factor of 3 of 1/3? So if you take a look at this function, first of all, you should graph the original function first, right? We should get negative 3, negative 6, multiply the entire thing by 1/3, which would give me my new function of negative x minus 2. And then to reflect it in the y-axis, okay, I only want to change the sign of x, not both, just x. So that turns into x minus 2. So my answer would be D. Okay. We did this in class. Okay. So to reflect it in the x-axis and translate it 3 units to the right, the answer to that would be C. The negative goes out front, and we have a minus 3. Okay. We will, this is a good one. Which equation represents the vertical translation? Vertical translation of 5 units up. That means I want to add 5 to the output of a function, so my answer would be H. Okay. Very good. That was 2-6, families of functions.